Hi everyone, I'm Kathleen Meyer, Marketing Specialist for Additive Manufacturing. Welcome to our webinar on DLP 3D printing and the benefits of open versus closed systems for 3D printing materials development. Thanks for joining today. A reminder that we will have a Q&A session following our presentation, so go ahead and submit your questions throughout the webinar. I'd like to quickly introduce you to today's presenters. Marshall Ling is the Swiss Army knife and a photopolymer expert at Origin. He works on various technical projects, including customer success, application development, and market research. Before Origin, Marshall worked at several metal 3D printing companies, including SLM, EOS, and Arconic. He has a bachelor's degree in aerospace engineering from the University of Texas in Austin. Andrew Graves has worked in the additive manufacturing industry since 1990, starting with 3D Systems in the UK and then in California. Andrew joined in 2017 and works to identify companies and technologies that enabled to provide complete solutions to its customers. Andrew was a 2015 recipient of AMUG's Distinguished Innovator Operator Award, including recognizing individuals for their years of experience and contributions to the AM community. With that, let's get started. I'd like to hand things over now to Andrew.
Thanks, Kathleen. I'd like to add my welcome to you all for attending this webinar with us and our partner, Origin. As Kathleen said, my name is Andrew Graves. I've been working, as she said, in additive since 1990, when 3D printing was so new that the biggest challenge was trying to explain to people what it actually was and why they would possibly need it. Excuse me. Chuck Hull had only invented stereolithography a few years earlier in the mid-1990s, and 3D printing was pretty much only used for prototyping in those days. The early resins for stereolithography, or SLA or SL, as we usually shorten it to, were based on either acrylate or vinyl ether chemistries. And they were okay for what we needed then because, well, quite honestly, they were all we had. But the parts curled and distorted and honestly broke into 100 pieces if you even looked at them in a funny way. Building large parts was a huge challenge because they curled, they shrank, and they distorted. Eventually, what we now call hybrid resins were developed, and these are a combination of acrylate and epoxy chemistries. And as many of you will know who have SLA systems, they give SLA parts great accuracy, great surface finish, really good strength, and low distortion and low shrinkage. And been supplying those hybrid SLA resins with our Somos brand since almost the beginning of this technology. We have a pretty large portfolio of different SLA materials, and we see the large frame SLA technology remaining valid for quite a number of years to come. But a few years ago, we started to see the DLP and the LCD 3D printers emerging, and like those early SLA systems, most of the resins available for these new printers are in fact acrylate based, or for example, acrylate urethanes or urethane acrylates, depending on how you want to term it. And you know, for building a lot of geometries, these resins are perfectly acceptable. But as DLP and LCD printers start being used in production applications, where part drawings, for example, are calling out accuracy and flatness tolerances, and especially as parts get bigger along with the printers, then more accurate resins are going to be needed. Currently, there are none of these hybrid acrylate epoxy resins available for DLP or LCD printers. So we're developing a range of engineered DLP and LCD resins based on a number of different chemistries, actually, including the hybrid chemistry, that are aimed at meeting customer application requirements for accuracy, toughness, heat tolerance, weatherability, etc. But we don't do this in a vacuum. We recognize that we're only part of the whole ecosystem. I mean, we only make the resins, right, or the materials. So we partner with a number of companies, printer manufacturers, obviously, post-processing companies, software companies, and even other material companies. And one of those that we've been working with for quite a while now is Origin. So I'd like to hand you over now to Marshall, who's going to talk about the OriginOne printer, our partnership, and a recent collaboration with us that led to a fast-track resin release. So over to you, Marshall.
Absolutely. Thank you, Andrew. I am Marshall Ling. I'm a technical account manager at Origin. And after Andrew's introduction, I'd like to sort of take a step back and explain our position in the market and how we differ from what you've traditionally seen in the additive manufacturing industry. So what you can see on the left is the structure of a typical 3D printing OEM, and they're vertically integrated, which means hardware, software, materials, they're going to own it all. And if you're printing with their printer, every single piece of what you're going to be using is going to be from that company. So we like to call that the razor blade, or the printer ink cartridge model, right? They're going to be many times subsidizing their hardware in return for recurring consumable revenue, whether that's from miscellaneous consumables on the printer or from margins on material. So vertical integration was very important earlier on in the advancement of the additive manufacturing industry. Whenever people are operating at low volumes and there aren't people like who we can partner with to provide us high performance resins, you have to do it yourself and you have to own that to generate the revenue you need to survive. So it used to be the only option really for many companies and existing OEMs who you're familiar with. Nowadays, as we move further into production, it actually ends up being stifling for a competition in many cases. So it leads to you having to single source your resin. Many times it'll be more expensive. You won't be able to get it from multiple places. It'll likely void your warranty. And so what we have transitioned to is more of an open additive manufacturing ecosystem. So Origin's one of the first industrial 3D printing polymer companies with this open platform material model. We believe that companies should own their competencies, right? So we recognize that we can really be experts in the hardware and software space and provide technologies and to these material companies. And we also recognize that these material companies have pieces of equipment or reactors that existed for dozens, if not hundreds of years, that are as expensive as the valuation of most of the 3D printing OEMs out there today. So competing with them to make production quality and production price resins is really not feasible for the industry. So what we do to align ourselves with them is taking zero margin on materials, and we're working to foster strong relationships with those partners and become the preferred development platform for our material partners. And what that allows us to do is become in complete alignment with those material partners and take those resins, take zero margin, and pass those savings directly to our customer. Because at the end of the day, if we're looking at that razor blade the business scheme, then if you're a consumer at the end of the day, if your razor head is a bit more expensive or your printer ink cartridge is a bit more expensive or worse performing, it's not the end of the world. But in a production environment, you should have the option to get that resin sourced directly from the manufacturer, have that lower cost, higher performance alternative, because it really does make a difference from that business perspective. So we'd like to go to the next slide here and talk about how we executed on this, and a good example of this for how we developed the QuickGen 500 material. So we had spoken with a variety of our customers and identified an application space where the materials available today weren't really able to fulfill the requirements to attack those applications. So some materials had the performance required, but maybe their throughput and price point put them out of the range of costs they would need to produce parts for the space. Or maybe they were able to use a less expensive resin, but some of the performance and perhaps the throughput was there and just wasn't good enough to hit those applications. So what we did is we came to DSM and we said, we need a general purpose resin. It has to be fast printing and fast post processing for this production scenario. It needs to be inexpensive. So we needed the resin cost to be sub $100 per kilogram. And we needed something that was colorless, had high elongation at break, and was very flexible. So was basically exceed what we expected in every single one of those categories in a very short amount of time. So once we came to, within a week, they had provided to us 7 different candidate formulations with printed final parts that were actually in the form that we needed to test to validate the application. So based off of that, we selected 2 of those initial resins and we said, these 2 look really promising, here's our feedback. So with one, we were basically ready to go and start the work for scaling and seeing if this was viable for production, while the other, we had a couple of quick things we wanted to change. So we wanted to increase the throughput. We wanted it to be a little bit less flexible, so a bit more rigid. And we also wanted it to be colorless where it had a bit of a tint. So they were able to actually, in the time it took them to put together the first samples of resin for us to recreate their work in-house, to iterate and adjust the formulation and match all of those requirements that we had. So at that point, we had 2 working resins for the application in-house. We requested actually more resin right off the bat to work on scalability testing. And once we took those resins in-house and started printing with them, we noticed with one, maybe it was a bit more difficult to clean, the material was tackier in the green state, while the other, which today is QuickGen 500, was phenomenal to handle, right? It wasn't going to be sticking to other parts in the green state. It was very quick to clean, very quick to post-process, very easy to print, extremely accurate. So similar materials in this application space will take 6 to 8 seconds per layer many times that we have to spend polymerizing, whereas QuickGen 500 is extremely fast printing. It only takes 2 seconds per layer to cure. So that happens while being an extremely accurate material with very little shrinkage or warpage, as well as having it being very easy to post-process and being a high-performance material, like you can see with some of these mechanical properties on the right side. And one thing that we really want to emphasize is that with this partnership and how fast we move, we did not cut any corners. So we didn't say, we need to get this to market, let's skip these steps that are very important, such as testing. And what really enabled that was both the expertise of people like Andrew here, who may not appreciate me bringing this up, but has been in the industry longer than I've been alive, as well as the technology that Origin provides that allows them to quickly and rapidly iterate materials. So on the next slide, we can sort of go through how the OriginOne enables scalable, consistent production. And after that, we can talk about how that plays into material development. So the bread and butter of our print process, which we call programmable photopolymerization, is actually our separation mechanism. If you are using a resin-based printer, you're always going to have to address the situation of what are you going to do about the parts sticking to the glass once they're polymerized. Many people introduce things like passive oxygen layers or just say stronger materials or rocking the bed, all of which either limit the number of chemistries that you can actually produce in the machine or result in high separation forces, which also limits what you can print. What we've done is we use a flexible separation layer of film, and our separation process, rather than ripping a part off of the glass or some sort of surface, is actually more akin to you peeling the really annoying piece of plastic you get when you buy new electronics. So you can imagine that the forces we impart on the part are very, very minimal, and we can perform this process extremely quickly. So what that results in is you being able to print geometries out of weak green state materials that couldn't be printed before, that are small, complex, really weak parts, without having to sacrifice print speed or just say, hey, you can't print that in our process. So we really afford our customers and our material partners the ability to print a wide variety of materials and a wide variety of geometries without making concessions on print speed, surface quality, or just what you can print in general. So the OriginOne is, as you can see in the middle here, 192 by 108 by 370 millimeter build volume, and it's sized for the application spaces that we're attacking and sized specifically for our customers. And we have a very high resolution printer. We use a 4K light engine. And what we've really emphasized with our product is that it is a production first machine. So we're specifically targeting high volume applications. And for that, the machine needs to be accurate, consistent, reliable, and repeatable. And a big part of how we do that actually is the simplicity of the DLP process, or the programmable photopolymerization process in general, right? So with typical tool-based additive manufacturing platforms, if you're looking at FDM, SLA, SLS, laser powder bed fusion, all of those, you're going to have some sort of nozzle or some point where the reaction is happening, and you're going to have to define a tool path. The entire reaction doesn't happen at once. It can require a lot of internal stresses to build. And if you look at the settings for some of these machines, it's several pages and 300 to 400 settings long. So what we have done is provided a process that is just as high performance. Once again, we don't have to make concessions on any of those performance aspects, while also we're able to simplify it. Everyone wants a simple manufacturing process. No one wants it to be complex. So what that does is it eliminates a lot of the potential for errors in our process and allows us to very accurately control and monitor what's happening. The settings in our machine number in the 20-ish range instead of those hundreds or dozens that other processes look at. It also makes it very easy for using the sensors in our printer to monitor every single thing that happens in that print process. And even though there's very little that can go wrong, assure that everything is going right in those areas. So like you can see on the right here, for every single print, we are constantly tracking the separation forces you induce, the temperature. We're able to control the environment of our build chamber. We're able to build pressure under inert environments. Print materials that are solid at room temperature but melt down as we heat both the resin and the chamber. And we're able to make sure that all this is happening the exact same across all the printers, across every single print. And we even monitor the rate of polymerization and the exothermic energy that's produced. So we try to lock down every single aspect and control every single aspect of the print, which is where the programmable photopolymerization comes from. And on this next slide, a lot of those things that I just covered and mentioned that are great for production are terrific for material innovation as well. So us working with the maximum number of chemistries possible has enabled our partners to bring materials to market that they were never able to utilize before on other platforms. And we have also enabled rapid material formulation, which we displayed with the development of QuickGen 500, like you can see on these two pieces on the right. So things that may have been dozens of prints before, we're able to print tens, hundreds of parts on a single build plate, all with varied settings, which really kickstarts the material development process. And that, coupled with our print speed and ease of development of settings and process optimization, allows our partners to develop the best materials they can as fast as they can. So overall, what we aim to be is a software-driven platform with robust but simple hardware that enables rapid development, consistent production, and the processing of exotic materials, which I know Andrew is very excited to talk about what's coming next. So I'll let him go on to the next slide and give you guys a look into the future with Origin.
Thanks, Marshall. So I think you can all see why Origin are part of our ecosystem and one of the great partners that we work with. But now I'm going to take a look into my rather cloudy crystal ball and talk about how we see the future of the 3D printing photopolymer industry. As I said earlier, we definitely see the large frame SLA printers been around for a while longer and new resins coming along for them as applications develop. Similarly, materials that are aimed at prototyping will be around for a long time, both in SLA and DLP and LCD. But we obviously see the huge growth in the DLP and LCD printer market, and especially those companies like Origin who are targeting actual production parts. And again, obviously, those applications are going to need more and, quite honestly, improved resins to meet the various property requirements. So some of these resins will be the acrylates or methacrylates, similar to the resins that are currently available. And we are indeed working on those resin families, but incorporating some unique custom formulated monomers and oligomers into the formulation to provide better mechanical properties, like the QuickGen 500 resin that Marshall talked about. We're also transitioning over our expertise from the SLA resins, that's the hybrid materials that I talked about before, the acrylate epoxy resins. And for larger parts, we see that the hybrid chemistry is going to play a major part in DLP and LCD in terms of lower curl, lower shrinkage, lower distortion, etc. But essentially, you, the user, the customer, you don't really care what the chemistry is, right? You just want a material that meets your application requirements, be that surface finish, accuracy, strength, weatherability, temperature tolerance, whatever. So our focus is on meeting your requirements with whatever chemistry makes sense, right? We also see the importance of open systems like the OriginOne. We believe that it strengthens the whole additive manufacturing market. The ability for our materials to run on as many printers as possible, and for the owners of those printers to run whatever resin makes sense for the production application that they're targeting. That could be resin this week for 2,000 of these parts, and then another company's resin next week for 1,000 copies of a different part. And we believe that this philosophy is what will help the additive manufacturing market really expand exponentially. So we'll continue to collaborate and share our thoughts and ideas with our partners and our customers, because to be honest, even after 30 years in this business, I'm still learning new things about it every single day, and it's still exciting, So with that, I think we'll have some time for some questions. Actually we've timed that quite well.
Exciting.
Thank you, Andrew and Marshall. We do have a couple questions. So Marshall, I'll start with you. What are the advantages and disadvantages of using two-part resins in 3D printing?
Absolutely. So when you look at single part versus two-part resins, our philosophy is always going to lean towards single part resins. And we do that for a variety of reasons. The first is that it's just easier to use single part resin. So as long as a single part resin can hit your requirements for the application, we're always going to push you towards that direction, just because of longer pot lives, less variables to control, less things that can go wrong in the manufacturing process. There's also some cases where two-part resins can be more volatile, so they'll lead to more shrinkage or warpage sometimes in the print, or maybe they'll be less safe because of more reactive components, more difficult to get into facilities and through EH&S. So those are some of the differences. Printing in two-part resins does give you some more tools to play with and work with. But what we've seen is that our material partners and their expertise have been able to hit the requirements for all the applications that we like to serve with single part resins. And all of our partners are terrific to work with and very talented and have been great at doing that. So thus far, we haven't needed to use dual part resins to attack any of the areas that we want to. And sort of the safety print process considerations will always make you lean towards a single part resin if one's available.
Okay. Andrew, what are some similarities or differences between SLA and DLP photopolymers?
Yeah, that's a very in-depth question, or at least the answer is. Essentially, they are very similar, very in a lot of ways. There's only a number of chemistries that you can use UV light to use a photoinitiator to solidify those materials. But the wavelengths that we see are one of the big issues. If people are familiar with the large frame SLA machines, they pretty much exclusively have a 355 nanometer laser in them. And for a number of reasons, some of which is historical, some of which is chemistry based. And then the DLP and the LCD printers tend to be the longer wavelengths. Sometimes 365 we're starting to see, but typically 385 to 405 nanometer. And that usually means, for a lot of chemistries, a different photoinitiator. So as I said, we are taking some of our SLA resins and thinking about where we could apply those to the DLP. And of course, we have to change the photoinitiator. it's not just as simple as taking one out and putting another one in. There's some reformulation requirements to that. But that's essentially, the theory is that you can get a similar performance of a material, whether it's on a DLP or an SLA. It's just that it's more convenient in a lot of ways to have it on a DLP because you don't have that large vat of resin. So I'm waffling now. I'm rambling.
No worries.
I'll stop there.
I think we could do a whole webinar on that, maybe.
Yeah.
Marshall, maybe this one's for you. So are Origin printers available globally, and could you maybe talk to the cost?
They are. We actually have printers right now in several countries around the world, and I'm not sure if I can talk about what all those are. But our printer is a lease for $100,000 over 3 years. So I think that should basically cover it. Was there anything else you'd want to touch on, Kathleen? Or
no, I think that answers that. Maybe we'll close with this question. So I'll start with Andrew, then Marshall, if you want to add anything, feel free to jump in. To what extent can a customer or OEM develop materials with suppliers? And I guess especially if they already have an Origin printer.
Well, we're very open to a lot of different business models and a lot of different ways of working. And if it all comes down to a business case, right? If there's a business case that makes sense for us to make money and the Origin printer company to make money and for the customer to make money, then we're always open to that discussion. Let's say we have a lot of expertise in materials, but we're always open to partnerships. If people have different ideas or they want to come and talk to us about that, I say essentially it's down to if it makes financial sense and there's a good business case behind it.
Yeah, I can add a bit to that from the Origin side as well. So a lot of our largest and most successful customers today actually have gone through this path that you sort of described. And whether that means reaching out to their material partner of choice and them pointing them to the Origin printer and saying, let's co-develop a resin to meet this application that you've described, or whether it's them coming to us and us choosing a partner to co-develop this resin. Like I said, our goal is to enable additive manufacturing and production. So any production opportunity that exists at scale, we and our material partners are going to be very open to co-developing or adjusting one of their existing solutions if required to hit the performance requirements that you have and to enable you to enter production with our machine and their resin.
Okay, great. Well, thank you again, Andrew and Marshall, for speaking today. Thank you, everyone in our audience, for joining us. We will be sending out a follow-up email with links to our websites and more information on how to get in touch with us. We look forward to hearing from you, and we look forward to working together on your next project. Thank you, everybody. Have a great day.
Thanks, everyone. Take care.
Thanks, Kathleen.